Today we're going to talk about a series, and a series is found very similar to a sequence. The only difference is that a series is the sum of a sequence. A sequence is divided by commas. A series will be divided by plus signs. So we have a bit of notation that changes, and that is with this sigma symbol. Anytime you see a capital sigma, it will mean to sum things up, to add up whatever is behind it. We have two kinds of series. They are either finite or infinite. So here I have a finite series, 3 plus 6 plus 9 plus 12. There are only 4 terms in the series. It ends at 12, so that is finite because it ends. Then I have an infinite series, 3 plus 6 plus 9 plus 12, etc., etc., etc. This one does not end because of the ... So to indicate that I am summing up these terms, I write my capital sigma. And around your sigma goes your upper and lower limit. On the bottom here is n equals 1 because I will be starting with the first term. On top goes how many total terms I am adding up. And I have 4 of them. So I have the first through the 4th term that I am adding up. Then we have this general rule that we have been generating for the last few days. That general rule is how you calculate the terms of your series, same as the terms of your sequence. And if you look at my rule, it reads 3n. So the first time you put 1 in there, you would get 3. Then you put 2 in, and you get 6. Then you put 3 in, and you get 9. Then you put 4 in, and you get 12. So it is 3 plus 6 plus 9 plus 12, which in the end then would equate to 40. Same goes with the infinite series. But notice, in the infinite series, again I started with the first term, but I go to the infinite term. So it is 1 through infinitely many terms. Notice I still have my general rule of how I'm going to generate each term within the series that I'm adding up. So it says, write your series with summation notation. That means using our capital sigma. So I have 4 plus 8 plus 12 plus etc. to 100. So first of all, I notice I am plussing them all. So I write capital sigma for what showing I am adding them up. And I am still starting with the first term. I do not yet know how many terms lie in the series from 4 to 100, but we will calculate that. But then let's look at the actual terms that are generated. From 4 to 8, what are you doing? Adding 4. From 8 to 12, adding 4. Adding 4. I am continually adding 4. So that generates the series 4n. When I put 1 in there, do I get 4? When I put 2 in there, do I get 8? When I put 3 in there, do I get 12? And the answer is yes. So I do not have to add anything else to that series. So I know to get this last term, I get it by calculating 4n. . So if I set 4n equal to 100, and then do the math, I get n equals 25. So 100 must be the 25th term. So then I come back here, and I am doing the first through the 25th term, and I am adding all of those together of 4n. Let's try our next one. Again, I see a bunch of plus signs, so I automatically put my sigma notation, my summation notation. And again, I'm starting with a first term. And this time, I have a finite series again, but I have the beginning and the end. So I can count how many of them I have. I have 1, 2, 3, 4, 5, 6, 7 terms. So I am going from the first to the 7th term. Now I need to see what pattern exists between my numbers. First of all, I see all fractions except the first one. So I'm going to turn this into a fraction of 1 over 1. Am I consistently adding anything to each term? 1 plus what gives me 4/3? That would be 1/3. Is 4/3 plus 1/3 6/4? No. So I am not consistently adding. It is not arithmetic. So let's check geometric. Am I consistently multiplying? 1 times what gives me 4/3? 4/3. Is 4/3 times 4/3 6/4? Again, no. So I don't have a geometric series either. So this is neither arithmetic nor geometric, but maybe I can generate a rule for the numerator and a different rule for the denominator. So if I look at just my numerators, 1, 4, 6, 8, 10, 12, 14, as they stand, they don't follow consistently. But if I change 1 over 1 to 2 over 2, do I still have the equivalency of 1? Now I have 2, 4, 6, 8, 10, and I am consistently adding 2, adding 2, adding 2, adding 2. So that would give me the rule 2n. Is 2 times 1, 2? Is 2 times 4, 2 times 2, 4? 2 times 3, 6. 2 times 4, 8. And it is working for my numerator. Now let's see what we can get in the denominator. 1, 3, it wasn't 1. 2, 3, 4, 5, 6. I'm consistently adding 1, adding 1, adding 1. So that would be 1n. Is 1 times 1, 2? No, it's 1, so I have to add 1 to it. 1 times 1 is 1, plus 1 is 2. 2 times 1 is 2, plus 1 is 3. 3 times 1 is 3, plus 1 is 4. And I get my series rule. Let's try another one. 2 plus 3/4 plus 4/9 plus 5/16. Again, I'd like to make this one fraction, so I'm going to change this to 2 over 1. And I'm adding them up, so I put my sigma. And I have a first term through an infinite term. This does not end. Now it's time to generate my rule. And again, I see this is a neither series. So on the numerator and the denominator, I'm going to have two different rules. Plus 1, plus 1, plus 1, plus 1 would give me 1n. 1 times 1 is 1. What do I have to add to that to get 2? 1. 2 times 1 is 2, plus 1 is 3, and that checks out. In the denominator, add 3, add 5, add 7. And as we learned earlier, anytime you're adding the next odd, it is a square. So n squared. Is 1 squared 1? Is 2 squared 4? Is 3 squared 9? So this would be my series rule with the number of terms summed up. How about if I give you the series in a sigma summation notation? Can you then generate the terms and find the sum? This should be a k. So we have k equals 5 to 10. So I'm not starting with the first term, I'm starting with the fifth term. The 5th through the 10th term. So I'm going to create my blanks. 5th, 6th, 7th, 8th, 9th, 10th term. And since it's a series, I'm going to add them up. So the first time I put 5 into k. 5 squared plus 1. That would be 26. Then I put 6 in. 6 squared plus 1. 37. Then I put 7 in. 7 squared plus 1. 50. 8. 8 squared plus 1. 65. 9. 9 squared plus 1. 82. 10. 10 squared plus 1. 101. And I have generated my series. However, since it is a finite series, at this point I can then calculate what that sum is. So if you would add that up, 26 plus 37 plus 50 plus 65 plus 82 plus 101, I believe you should get a total of 361. So this would be generating my series from my series notation and then giving me the final sum of that. So when I say S sub 6, I mean the sum of 6 terms. So here'd be another way. The sum of the first 6 terms generated by the equation 2n minus 1. So in series notation, it would be n equals 1 to 6 of 2n minus 1. So again, I have 6 of them. 1 plus 2 plus 3 plus 4 plus 5 plus 6. 2 times 1 minus 1 is 1. 2 times 2 minus 1 is 3. 2 times 3 minus 1 is 5. 2 times 4 minus 1 is 7. 2 times 5 minus 1 is 9. 2 times 6 minus 1 is 11. This would be the series. Now I just need its final total. 1 plus 3 is 4, plus 5 is 9, plus 7 is 16, plus 20 is 36. Let's try the last one. Still adding up 6 terms, so it would be the summation of 1 to 6 terms of 2n squared. So this time I have 1 plus 2 plus 3 plus 4 plus 5 plus 6 terms. So this one will be 2 times 1 squared is 2. 2 times 2 squared, 4 times 2 is 8. 2 times 3 squared, 9 times 2 is 18. 2 times 4 squared, 16 times 2 is 32. 2 times 5 squared, 25 times 2 is 50. And 2 times 6 squared, 36 times 2 is 72. Here's my series, and that all adds up to this part is 10. This is 50. So here's 110, 182. See how to write using summation, sigma notation, and then finding the sum of all those. You could just add them up. Now we do have some special rules that will calculate the sum of different series, and I really think there's only a couple here you need to know. Some of them I think just make complete sense. This one says when I'm going to add up terms of some rule times a constant, it simply means take the constant times the sum of the rule. So an example of that would be the sum of 1 to 10 of 6n. I could say that's the sum of 1 to 10 of n and 6 times all that. It would give me the same answer. This is saying when I sum up the sum of two rules, it should make sense to you that it could be the sum of the first rule plus the sum of the second rule. That just makes sense to me. So then this one, when I sum up the difference of two rules, it could be the sum of the first rule minus the sum of the second rule. This one is saying when I sum up a constant. So let's say I just add up 1 to 10 sixes. Well, that means I have 6 plus 6 plus 6 plus 6 10 times. I have 10 sixes. So it says take how many you have times your constant. Isn't that what I had? 6 plus 6 plus 6 plus 6 10 times. 10 sixes. So this one I think makes common sense. This is one you can use often. Now this would be a rule I would know, but tomorrow I'm going to teach you a different way to do it, so I don't even necessarily always bother with this one. The sum of n number of terms where I'm adding up the first however many terms. So for example, the sum of 1 to 10 terms of n. So it would be 1 plus 2 plus 3 plus 9 plus 10. It says take the first term, however many you have, times one more than that and divide by 2. So this would be 10 times 11 divided by 2 would give me 5. This should all add up to 55. And then this is one I would know. From 1 to n of I squared. So what it means is I'm adding up the first however many squares. This is what you do. You take how many you're adding up, plus one more, or times one more than that, times 2n plus 1, all divided by 6. N times n plus 1 times 2n plus 1, all divided by 6. So here are a few examples of those special rules. I'm adding up the first 15 terms of 4n. So again, I see a constant times a rule. So I could take the constant times the sum of the first 15 terms of just n. Now, I'm here at this rule. So it means 4 times, I'm adding up 15 times 1 more divided by 2. That makes this 8 times 15 times 4 should give me a total of 480. Those rules help me get my sums much quicker rather than writing out 15 of 4 plus 8 plus 12 plus 15 times. This one says I'm adding up 1 through 115 threes. So this means 3 plus 3 plus 3 plus 3 till I get to the 115th one. Doesn't that mean I have 115 threes? Which gives me 345. And this last one combines two rules that I'm subtracting. I'm subtracting the squares and I'm subtracting the all the first terms, 16 of them. So this means I could have 1 to 16 squares minus 1 to 16 linears. So this says, right here is the rule, n, which is 16, times 1 more than 16, which would be 17, times 2 times 16, which would be 32, plus 1 would be 33, all divided by 6, minus 16 times 17 divided by 2. So when I put that in my calculator, I should get 1,360. Just a quicker way to add those up rather than writing 16 of those terms into that rule.